even if some of it's frustrating.
Yeah. Jesus is much better.
Okay, let's get started. Just a heads up, I did put in a ticket for this thing. I don't know if they've done anything with it yet. We'll see if it's better, but at least somebody who's supposed to fix that stuff knows about the screen flickering. So we'll see if it's possible they came and tweaked it or something, but I haven't received any notification. All right, so let's power through the rest of this history of language stuff, which should map up to kind of where we are in the book. And over the weekend, I'll give you the rest of chapter 1 here in the book. I think you just finished, 1.7? Okay, so I'm going to give you 1.8, 1.9, and 1.10 over the weekend so that on Monday we can start programming. Okay, these aren't too long. One thing I would recommend, though, is if you didn't follow along in 1.6, follow this and get a development environment set up for Python. So get something on your computer so that you can actually write some Python stuff. I will also put up a link in case, how many of you in here are using a Mac? Okay, I'll put up a link that kind of takes you through getting it on a Mac. I'm actually going to demo it on a Mac. It's the same thing on both. It's actually easier to get going on a Mac. So, but they're both not bad. Okay, so we've talked about all this number conversion stuff. We've kind of talked about the different kinds of programming languages from a couple of the different angles. So what I want to do now is kind of see where does Python fit in the big world of kind of the history of programming languages, starting at the late 1960s, so around when the C programming language came out. And I want to talk about the evolution of those languages, kind of putting in context some of the things we've already discussed, procedural languages versus object-oriented languages and that kind of stuff. Remember we talked about like the procedural telephone pile of wires versus the object-oriented telephone that actually looks like a telephone. Okay, so putting some of the stuff we've discussed in context through the history of our languages. All right, so that's where this picture comes from. So we have, I'm going to label these two sides here. I'm going to call these guys web languages. And I'm going to call these guys native languages. Okay. So notice here that Python is actually over on the web languages side of things. Okay, so one thing we can kind of say, so let me just read the languages off here. So at the very top level, we have the C programming language. All of these languages here, at some level, came from C. They took a lot of stuff from C, and we talked about that a little bit when we talked about the primitive types, ints, so the various ways of holding whole numbers and things like that. We also had on the primitive types, we had floats and doubles, so those are decimal point numbers, but a pretty similar argument where a float is kind of like an int, a double is kind of like a long, so they hold different size values that can hold decimal points, so like 3.14, stuff like that. And then we have this thing called a Boolean, which holds true and falses, which we'll talk about in more detail as we go on. But punchline is all of our modern languages at some level came from C. And in most of the cases, strongly came from C. Go ahead.
So then why don't most people start learning C? I mean, like Java and Python are probably 2 weeks down.
I mean, it's a reasonable argument. Some more traditional programs, let's say older programs that haven't updated, probably still do introduce C early on. One of the dangers with C, and we'll talk about it here in a few minutes, is it kind of allows a beginning programmer to run into a bunch of memory leak problems and stuff like that. So C is a pretty powerful language, but it kind of gives you access to things that are maybe a little bit dangerous and not all that important for beginning programmers, to the point where now it's inconvenient to learn it, because you're having to anymore you don't have this issue, but certainly back in the late 90s, early 2000s, I mean, you could legitimately, writing a simple program in C, crash your operating system and then have to restart your computer in order to continue with your homework. because now things are usually protected inside of like virtual machines or protected memory or something, so that's less dangerous. But punchline is C is kind of inconvenient as the first language. We do go back in the 450 class here. We use C and C++. So it's not that it's a bad language. In fact, we'll see examples of C throughout. In fact, when you look at Java and C# and then you go back and look at C and C++, you're going to see vast similarities. Okay, and we'll talk about kind of the differences as we go through here. But over here in the native languages, so these, almost every one of these languages over here are, in fact, every one of those languages over there are compiled, strongly typed, let's just leave it at that. So they're compiled and strongly typed languages. So these would be the languages that we've been describing as relatively fast. Make sense? Where over on this side, these languages are interpreted, loosely typed, and relatively slow. Keeping in mind that computers are really, really, really fast, so don't worry so much about that relatively slow and relatively fast thing. It only comes into play under certain circumstances, like if you're writing a video game, you're probably going to use a native language because you want it to be really, really, really fast. Okay? Where if you're writing a word processor, okay, or some business application, nobody sits there and says, I'm running Microsoft Word at 130 frames a second. Start doing that around your buddies who are gamers, and somebody's going to slap you. But that's not what we brag about, right? We don't measure the performance of your business applications in terms of frames per second or frame rate. Okay, but if you're a gamer and you're bragging how your graphics card is better than your other friend's graphics card, well, then you care about frames per second, right? That's what you're bragging about. All right, so interpreted, loosely typed languages are relatively slow, but they're very, very, very viable for a lot of things. Okay, so don't look at them as lesser languages. Native languages are compiled, strongly typed. They happen to be relatively fast. They're very, very, very good for specific tasks, and they are nothing special compared to the web languages for many tasks. Okay, so generally speaking, as if you think back to your 150 class in computer science is problem solving, and what are we? We become expert problem solvers from the perspective of we are going to use computers and various pieces of software either already written on computers or software that we write ourselves to solve a problem in the best possible way. Okay, that doesn't necessarily mean that the best solution is to use a native language. It might be the best solution to use a web language, specifically Python. Maybe today, if you're doing data science or some artificial intelligence stuff, there's a lot of libraries built into Python for that type of stuff. So that might be kind of your go-to language for that, because it doesn't necessarily need to be crazy, crazy fast. It's really performing a task that a human being couldn't do on their own, or would be very inconvenient for us to do on its own. And it just happens to have some cool features that make our life easier, as opposed to maybe like a language like PHP, which is just as good as Python or Ruby or something like that. We'll talk about those. But at the end of the day, it doesn't have a lot of the AI and data science stuff built into it. So you could write it yourself if you wanted to, if you were just really dedicated to using PHP, or you use the right tool for the job. Okay, and that's actually, I don't want you to take that those last couple of comments lightly, because this is going to be an important part of how you will proceed as a computer science expert. Okay, the idea is I don't want any of you to fall in love with a language to the point where you see the solution to every single problem through that language because that's all you know. Use the right tool for the job. Once you learn computer programming as a skill set, which is what we're going to be focused on, already focused on it, but we're going to continue to focus on it, you can learn the technology that you need to learn quickly. You know, there'll be a little ramp up period as you're learning the little intricacies of that language that you haven't worked with before, but you're going to see vast similarities between the languages because they all came from C. That make sense? All right, so use the right tool for the job, not the tool you're most familiar with. Okay, even though at home, sometimes we don't necessarily follow that rule, right? There's the correct tool for the job, but we can fix anything with a screwdriver and duct tape, whether it was built for that tool or not. Okay, so, you know, so some of the things some problems you've solved at home, you know you can go to Home Depot and spend money to get the right tool for that job, or you can just hack it and figure out some solution to it. So I guess pick your poison. All right, so on the native language side of things, we start off with language here at the top called procedural. It's called C, and it's a procedural language. C is not the first programming language to exist, but we're going to say by today's standards, it's the first language to matter. All right? You know, I'm sure you would find some people that might argue with that a little bit. Maybe they'd go back a little farther and talk about, well, actually not even farther. They go to a language like Smalltalk, which is a, let's call it the first object-oriented language that had a lot of influence on future languages, but I think it's fair to say that C is the core of all of our modern languages. All right, so let's talk about what C gave us. All right, now just as a quick reminder, how do human beings solve problems? We use our memory, we ask questions, and repetition. And I mentioned that 100% of programming languages will have facilities for those three things. It'll be able to represent memory through variables, is usually what it's called. It'll be able to represent asking questions through conditionals, usually if statements. Why if statements? Because that's what came with C. All right? If you go back to an older language, maybe a conditional is like the keyword cond, C-O-N-D, or something like that. But C uses if statements, so most of our modern languages use if statements. All right? And then lastly, repetition. We have loops and the ability to write functions, methods, procedures, subroutines. Sometimes there's different names in different languages, but they all mean the same thing. Okay, we'll talk about that stuff. All right, so here is the, let's call it the 10,000-foot view of C. What did C give us? C gave us variables, and it gave us loops, and it gave us functions, so, you know, we can throw those in here too. So we have loops, we have conditionals. Actually, let's just put them all on one line so the text doesn't get too small. And it has functions / procedures. All right, so it has all of those core components that I say that all programming languages must have. Okay, comes with it. All right, then C has this concept called an array. We'll talk about arrays in here. We're going to actually call them lists in terms of Python, but these guys are just collections of like types. Okay, if I want a whole bunch of integers, I can create a single variable that can hold a whole bunch of integers instead of just one integer. Those are called arrays. All right, then it has this thing called a struct. Now the problem with an array is I can have an array called favorite numbers. And maybe inside that array I have my 100 favorite integers. Probably random generated because you probably can't come up with your first favorite number, let alone your top 100, right? But let's just say I'm weird. And I actually do have a top 100 favorite numbers, but I could have a single variable. So for example, in C, I would write something like int array AR is equal to a new int array 100, something like this. And this would be a single variable named AR that would have space for 100 integers. Now, I wouldn't be able to differentiate between the different integers in terms of what their meaning was. I would just be able to say, give me the integer at bucket 7 of that array. Give me the integer at bucket 19 of that array, so on and so forth. It's just a big bucket, big collection of integers, where each integer is just as good as any other one. Okay? So that's what arrays are, collections of like types. Now, C also gave us this thing called a struct, all right? And this is kind of short for data structure. And we talk about that in the 300 class a lot more, but it's just a fancy name of saying now we have a single variable capable of holding more than one name-value pair. Okay, so for instance, we can have a struct, maybe called person, where a person has a first name, they have a last name, and maybe they have an age. Okay, so we have a collection of values similar to arrays, but those values do not have to be identical in type. They don't have to be a bunch of integers or a bunch of chars or a bunch of floats. They can be, in the example of a person, maybe we have a first name that's a string, a last name that's a string, and an age that's an integer, something like that. Okay, but it also allows us to label those things. So we can create a structure called person and say, this guy, we're holding a collection of three things. We want a first name, and we're going to store the first name. We want a last name, store the last name, and we want an age, store the age. Okay? Structs let us pull that off. Makes sense, right? Okay? So C gives us that type of thing. All right? Now, we're going to call this line here the weakness with structs. That is, structs do not allow us to embed functions. So I can have a person, I can represent a person by their name and their age, but it can't do anything more than that. It's informational only, not functional. Okay? So now, generally speaking, now keep in mind, this was not a problem for a long time, really, because I'm mentioning C came out ballpark 1968. Okay? Long time ago. And we've already talked about cost of memory. We talked about cost of memory in like the late 90s, right? Mid 90s, something like that, where that 8 megabyte chip was $1,000. Okay, expensive. How much do you think memory was in 1968? And how much smaller than 8 megabytes do you think it was? A lot more expensive and a lot smaller, right? You might have had a computer that you had to work with 4 kilobytes of memory, and that 4 kilobytes maybe cost $40,000. Not a lot of room to work with, right? Okay, so do you think the programs that we wrote back in the late 1960s and early 1970s were anywhere near as complex as the programs we can write today? No, we had less wiggle room. Our languages weren't as powerful because they didn't have to be as powerful. Even though I'm saying C is a very powerful language. You just weren't really able to take full advantage of what C would be capable of as a language because the underlying hardware that you were writing for wasn't up to the task. It was still much better at doing fast math stuff than a human being is. It didn't get tired, didn't make mistakes, could still do millions of calculations per second, or in the early days, let's say hundreds of thousands of calculations per second. Now we can do billions and billions and billions of calculations per second, but anyway, you cut it faster than a person, okay? But for a long time, C was a good enough tool because the programs we were writing were much less complex than the programs we write today. And I've already talked about how the programs that we write today are trivial compared to the problems that human beings solve on a daily basis, okay? Which is going to make you feel bad about yourself when we start doing the programming assignments and these really simple problems you're going to spend 10 hours trying to solve and not get the solution. And all of a sudden, I'm going to say, okay, we'll just solve that on paper, and you can just do it in 10 seconds. Like, well, that's this. Well, now write the code that does it. It's a little bit tougher. All right? Kind of like when I travel quite a bit. If I go to one of these foreign countries and you end up in, I like to go to the restaurants where the natives eat, not the commercialized places. And a lot of times they don't speak English there. So it's a pretty interesting task when I'm trying to order food in a language that I don't know. And that it's just kind of a coin flip what you get. It's actually really more of a 100-sided die roll of what you get, but it's usually pretty fun. Same type of thing though, okay? You'll be able to solve a problem as a human. I know what I feel like eating, but I'm not able to tell the computer what I actually want. Make sense? There's that translation. Something's missing in that translation. That's what the skill that we're going to be practicing this semester, putting those reps in. Okay? So keep in mind that we don't want to look at C as being a weak language because it is actually still used today. Okay? But as we started getting to problems that became more and more and more complex, we started noticing little, probably the biggest issue with C, we could say, is that it didn't, well, object-oriented programming wasn't invented yet, let's say. But as our programs got more complex, we started needing something like object-oriented programming in order to keep ourselves sane. So when we created a telephone in C, for example, we would have this giant pile of wires that looks like a big mess. And having an object-oriented version of that would allow us to hide all those details that we don't need to work with again and only expose the parts that we actually are going to use. Okay? So it gave us another level of organization. And then, as I mentioned before, C, as well as C++, gives us direct access to computer memory. And as a beginning programmer, I promise you, you're going to have far more errors than you wish. And in C, those errors could be dangerous and make you have to reboot your computer and stuff like that because you put your operating system in an unstable state. So we can also say that C and C++ are maybe not the best learning languages in terms of being forgiving. Maybe that's the better thing. Almost like a golf analogy. When you take up golf, there's like game improvement clubs you can get where you can like hit the ball way off center and still sort of kind of function. And then you have like these blades that the pros play with that you either hit it in the sweet spot or the ball goes nowhere. And when you start, you use the game improvement ones, and if you kind of suck, you look better than you should have, right? C is more like those blades, where maybe we want more of the game improvement type of thing, and Python's pretty good for that. All right, we can't get in too much trouble with an interpreted language in general. All right, so then, I think our quizzes are going to be interspersed in here because I just drug them down in different places. All right, so let's see where we at here. All right, so I'm going to steal this guy here. Oh, sorry. All right, so then we introduce C++. C++ still has variables, still has loops, conditionals, functions, procedures, blah, blah, blah. Still has arrays, still has structs. But what it did is it introduced the idea of a class. This is object-oriented. Okay? A class is a struct that allows us to have functions in it. Okay, so now a person, we talked a few minutes ago about a person struct, that's just a name and an age, but now a person could also do things, add two numbers together. We can say person P dot add two numbers together, 3 and 5, and he comes back with an 8. Okay, they could do magic tricks now. All right, before we would have had to write separate functions, separate abilities, and then pass person structures to it. Okay, and tell them to go and have them operate on it. Now we can embed those guys inside of classes. Okay, so we can think of a class as kind of a super struct. That's only a half truth. At some point, I'll be able to show you an example of this. But when we talk about Java here in a minute, it's actually a mistake that the Java folks made. And I'll bring that back up then. All right, so sorta, kinda. In fact, in most ways, we can think of a class as being a superstruct. It's a collection of name value pairs, and then it also can do other things. Okay? Now, what was the weakness with C++? Let's pretty much throw it to the whole memory thing. Again, powerful language, basically equivalent to C in terms of power, except we've gained that class ability, the object-oriented side of things, but still was maybe not the friendliest game improvement language for beginning programmers. Okay? Still super powerful even by today's standards. C++ is a great language, but it is not forgiving. Okay? Then, we look at Java. Okay, if you remember, we're just going down our list here from the picture. Okay? So we look at Java. Java still had variables, still had loops, conditionals, functions, and procedures, still had arrays, got rid of structs. But kept the class. Now, one other thing Java did was they reduced the amount of syntax. Yeah, let's just leave it at that so the text doesn't get too small. So they reduced the amount of syntax. There are plenty of examples in C, C++, Java. Let's just use C++ as an example, where you would write a class and certain aspects of the code always look identical. 100% of the time, it's the exact same little text that you have to put in there every single time you write a class. Java said, well, if you always write that, let's not make you write that. We'll just do it for you in the background. So it reduced some of the typing you would have had to do. Okay? We're not talking about ridiculous amounts, just little things. Okay? And when we get to some of those things, I'll show examples of that, but I'm just kind of giving you the big picture here. Go ahead.
That, so doing stuff in the background for you, that would happen when it's compiled, right?
That's probably a fair statement. Yeah. There's some other stuff going on too. Not just when it's compiled, even during runtime, there's something called garbage collection. Automatic garbage collection where it cleans up memory for you. Or in C and C++, if you created new memory, you were in charge of cleaning up your own room. The idea would be that you should always clean up your messes. Java said, we'll clean it up for you. No problem, right? But then what does that do? That trains us to be lazy programmers. Then we ran into problems when mobile application development came out. Because you had all these programmers who were used to being lazy. Okay, I'm kind of a stickler for, and I'll kind of show you as we start writing some code, I'm a stickler for making sure you write things in the correct way, not just necessarily in a way that will work. And I'm not talking about the solution to the problem. I'm fine with weird solutions to a problem because that's just how your mind is going to think early on. But when you write something and you omit a line of code that really is necessary, but it just happens to work without that line of code, from a new programmer's perspective, you think, oh, that line's not necessary, it just works. When the reality is you're making the computer either do extra work in the background or now your program has a memory leak in it because you didn't clean something up. And what did you do? Well, you just wasted some memory, and now that's memory that can never be used again on your computer until the next time you reboot it. Who cares? You got tons of memory, not a big deal. But now you're a sloppy programmer. Does that make sense? So the more modern languages let you get away with a lot. And that can be somewhat dangerous. So that's another reason why I like to, across our classes that you'll have with me, I like to bounce between languages quite a bit. So you're put in those uncomfortable situations where like, well, this worked in such and such. It's like, well, it didn't really work in such and such. It just didn't complain to you. Okay, you were still bleeding. You had internal bleeding still. You just didn't notice. Okay? But punchline is Java hid a lot of the stuff from us. It did a convenience for us. But using Java as your very first programming language actually is somewhat, I think, of a problem. Even though we can say Java is friendly from a game improvement perspective, that is, it's you screw up, it's not going to crash your computer or anything like this. But since it hides so much stuff from you, it's easy for a beginning programmer to assume certain things just happen by magic, when there's actually some legitimate stuff that's happening behind the scenes that we go back through and talk about. Make sense? All right, so, and we'll see plenty of examples, so I'm giving you the high-level version of this. So Java had a goal of reducing the amount of syntax here. Okay, so now the problem with Java, I'm just going to be kind of vague here, but we're going to say relatively slow. And then I'll also throw in there misguided maybe. And this is still true today. I mentioned that they made a mistake. and this goes back to this previous slide when we were talking about structs versus classes. So notice that in Java, we got rid of a struct. A struct is a collection of name-value pairs. Okay? First name, Mike. Last name, Littman. Age. Okay, so on and so forth. A class is a collection of name-value pairs plus the ability of having functions. All right. So, is it fair to say, could it be fair to say that, well, haven't I actually accomplished the same thing as a struct if I write a class and then choose not to write any functions? If a struct is a collection of name-value pairs and a class is a collection of name-value pairs plus potentially functions, couldn't I choose just not to write some functions and now I basically have a struct? That's what the Java people thought too. All right. The answer is mostly yes, but this actually goes back to things from C and C++. By default, if you're passing a struct or passing a class to another part of your program, I don't want to get into too many details with it, by default, structs are passed by value, whereas classes are passed by address. All right, and we'll talk about this a lot more later, but let me give you a practical example of this. We were talking about a person struct before, right? Okay, so I have a, and it's kind of a weak representation of a person, right? I just have a little note card, let's say, and I write their name on and their age on. Not too heavy, right? And I can go and hand that actual note card to any of you, and that's not going to be overly burdensome, right? Now, when we move to the class version of a person, now we're truly trying to represent an actual person object. Okay, that's a name, that's all these abilities. So let's say each one of you knows how to do millions and millions and millions of different things. All right, so we'll take whoever's the lightest person in here, let's just say it's 100 pounds. Okay, so a person weighs 100 pounds. Now, if I'm handing another part of my program a person, would we want to hand them a 100-pound thing? If I was giving you, let's take it away from like human trafficking here, and let's say there's a TV set, okay, big screen TV, okay. Now we all want a free TV, right? But assuming you're going to get the TV anyways, would you rather me bring the TV to class and hand it to you at the desk, or tell you that the TV's waiting for you in the mailroom, where you can go and find the TV? That's much more convenient, right? That way you can get some buddies together, go and pick up the TV, whatever. Okay, so when we start thinking about the amount of memory you might use for different things, certainly a person object is going to have a lot more memory associated with it. It's going to be a lot heavier than a person struct. Okay? Now, we're going to say that a person struct, because it's just a whole bunch of information written on a note card, for example, is light anyways. It doesn't really matter how much memory it's taken up. It's not going to weigh 100 pounds, right, in our human version of this. So passing a struct by value is probably always okay. I can give you the actual note card every single time. Sometimes it's a little bit thicker card stock, or it's a little bit bigger piece of paper or something like that, but you're going to be able to handle it without it being like a destructive part of your day. All right, but as we start getting to objects that have lots and lots and lots and lots of stuff in them, you might have an object that is 30, 40 megabytes, or we could say 100 pounds. Now that's something where it might make a whole lot more sense for me to give you the 32-bit or the 64-bit address where you can find that guy. Okay, I left the TV in the mailroom, something like that. Okay, so give me that little slip of paper with the mailbox number it's attached to or something like that is lightweight compared to the 100-pound TV. That makes sense? So objects, classes, are always passed by address. I always give you that little slip of paper that says where you can find it. Structs are always passed by value. I always give you the actual note card that has the name value pairs on it. Now, most of the time, are both TVs off? Okay. Well, whatever. Most of the time, this might not come back to haunt you. Because a lot of the times when you're writing code, it might not necessarily matter to you, depending on what you're doing with it. I'm not going to be able to give you great examples of this until we kind of get to this stuff. But let's call it 98% of the time, you might not notice the difference. But every now and then, you might try to do something in your code where your code would behave differently when something is passed by value versus when something is passed by address. Beginning programmers, a lot of times, are guessing, okay, until you get more advanced and you understand the difference between passed by value and passed by address and what that ultimately means. So in a language like C++, you might legitimately take advantage of the fact that structs are passed by value. Similarly, you might take advantage of the fact that objects, classes, are passed by address. In Java, we no longer have that pass by value version of a struct. They've basically said, oh, if you want a struct, just write a class that doesn't have functions in it, just a bunch of name value pairs. And 98% of the time, that's going to be okay. But technically, it's still a class, so technically it still gets passed by address, not by value. So it does not act identically to structs. That makes sense? So they've really taken away a feature that even though you can mostly accomplish the same thing through a cut down version of a class, it isn't functionally identical all the time. Situational, but maybe a little dangerous for beginning programmers. Because the punchline there is when something's passed by address, if you change it, it's changed globally everywhere that ever existed. When something's passed by value, you can change it and it's just you have a local copy of it. So there's not side effect to your changes. So it does matter. Okay? And we'll see plenty of examples of that. But we can say that that's a little slip up that Java made. But maybe the bigger issue is kind of the relative slowness aspect of Java. So Java came out, it's made by a company called Sun Microsystems that has since it's no longer a company. It was bought by Oracle. So, but back then, Java came out to save the world, so to speak, from the computing industry, because a lot of times this was mostly the gamers screaming, and it was really mostly the Apple gamers that were screaming, if that exists. But they were saying, hey, game or software XYZ comes out for Windows, but not for Mac. Because when you wrote it in C++, a compiled language, you had to rewrite it a second time, or mostly rewrite it, to work on Mac. As we saw, first couple days of class, we looked at that assembly language code. Okay, that would have been the output of a compiler. And remember I said that guy uses a bunch of, we wrote hello world in a Linux assembly, right? So that was the output of a compiler. And that guy had power tools in it, where he was using system calls of the Linux operating system. So if you were to write a video game in C or C++ and compile it for Windows, that's going to be using various system calls of the Windows operating system. That's not going to work on a Mac, because a Mac has different system calls, and some system calls might not even exist. So at the very least, you're going to have to recompile the C code for the Mac operating system, and very likely you're going to have to make some major changes. Especially back then, when most games that came out were written using something called DirectX for 3D graphics. Well, even 2D graphics. It was called DirectDraw for 2D. DirectX is 3D. But DirectX is a Microsoft product only available on Windows. So if you created all the graphics for your game, all the animations, all that stuff in DirectX, you're rewriting all of that on the Mac using OpenGL. Okay? So punchline is most games came out for Windows and either never came out for Mac or were significantly delayed, a year or more, something like that. So obviously the Mac people are like, well, why don't we have the best games? And then you would say, oh, well, why don't you just get a PC? right? And run Windows. So the original idea of Java was a good one, because Java is something that's called platform independent. Write once, run anywhere. So when we have a Java program, what's actually getting created, we have this thing called the JVM. That's the Java Virtual Machine. You can think of that as kind of like a DVD player, okay? Blu-ray player or whatever. Okay, so we have a JVM written on Windows. We have a JVM written on Mac, written on Linux, written for your phones, all right? The JVM knows how to play Java programs. Make sense? So you write the Java program once because you're writing it in terms of the Java virtual machine. And then what they did is they made the Java virtual machine for all of those different platforms. So you wrote your program once, and then it ran on every single platform without you changing it. On the surface, that sounds like a good idea, right? And it is a good idea. Beginning of class today, we mentioned that, hey, a lot of our applications, speed isn't overly important. We're not bragging about Microsoft Word frames per second. All right, so this is great for business applications. In fact, it revolutionized the kind of stock investing world, because now you can go to like E-Trade or Ameritrade or any of these things, and you can buy into their like professional investment tool, and this giant real-time day trading platform launches out of your web browser. That's a Java application. All right, it's great. It doesn't matter what kind of computer you're on. You can do it on Linux, you can do it on Windows, Mac, whatever. So it's perfect for that kind of stuff. But its original motivation was, hey, now the games will come out quicker. You don't want your games written in Java, because Java is relatively slow compared to C++ and C, which are compiled natively for that operating system and that hardware. It's still going to be faster than like Python. Okay, but again, I don't want to harp too much on this relatively slow, relatively fast thing, because computers are really, really, really fast. So it only is going to come into play in the extremes. Okay, gaming happens to be one of the extremes. So our video games are not written in Java. Games like Angry Birds could be. All right, fun little games. Nobody's saying I'm running Angry Birds at 130 frames a second. You're not measuring Angry Birds that way. Make sense? So anything that you would brag about frames per second for needs to be written in a native language compiled for the hardware. So that's C, C++, or as we'll see here in a second, C#. C#. Still had variables, still had loops, conditionals, functions, still had arrays. Brought structs back. Okay. Now, there's one thing I kind of took out of here. I didn't mention. I'm just going to mention it at the high level because we cover it a lot more later on. But in C and C++, I've kind of mentioned that it gives you direct access to memory. Okay. And that's through something called a pointer. Java removed that ability. You no longer had direct access to memory, so you couldn't get into trouble. Now, punchline is that sometimes advanced programmer wants direct access to memory for a good reason. Well, Java took that away from you. Okay, they took away the cookie jar. Well, what C# did is they said, okay, we're going to give you pointers back. Pointers do exist in Java. We'll see it. You just don't have a special syntax for accessing them. Basically what happens in Java, they just make the correct decision for you. And 99% of the time, it is the correct decision. But every now and then, you really want to mess with memory. Might be for a good reason, might be because you're a noob. Who knows, right? Java took that away. C# brought it back, but if you're going to manipulate memory directly, they make you put it inside of a code block called an unsafe code block. they make you specify to the compiler, like, look, I know what I'm doing here. I realize that I'm putting this memory stuff inside of something that says it's unsafe. So I'm vouching that I know what I'm doing. Okay? Or I'm willing to play with fire. One of the two. Make sense? So we could say in general that C# brought a lot of the stuff that Java took away that really did have a place. But it still had most of the advantages of Java. The other thing we can take off here, though, is C# is not relatively slow. C# took Java's write once, run anywhere model and changed it just a little bit. Where the very first time you run your C# program, it compiles it natively for that program. So while Java is platform independent, that is to say it'll run on any platform that has a version of the Java virtual machine, Microsoft would say that C# is also platform independent. It'll run on any platform that supports the .NET component architecture. But if you read between the lines, they're basically saying it's platform independent. It'll run on any machine as long as it's running Windows. This .NET component architecture is only available on Windows. But if it were available on other platforms, C# would work on there. And now they've been porting it over to the Mac, so you can do some .NET stuff on the Mac. And for a while, we had this hack project called Mono Develop, that would allow you to do C# on Mac and Linux using kind of a cobbled together thing that was supposed to be equivalent to the .NET component architecture. Microsoft's .NET component architecture is not open source, so everything's closed. We can't see it. We can't see the source code. So they had to make guesses at how it was implemented and create the equivalent libraries for Linux and for Mac and that kind of stuff to make things, let's say, mostly work. But it was not a convenient type thing. Okay, so Microsoft was very Microsofty there, where they said, still platform independent as long as you're running Windows. Just run our platform, and it's platform independent. Okay? But C# does have a lot of cool advantages over Java from a speed perspective. And C# probably wouldn't even exist if Microsoft hadn't acted like Microsoft, or replace Microsoft with any other big company. Because way back then, what did Microsoft do? When Java first came out, everybody was really excited about Java. So of course, Microsoft tried to steal Java, right? We talked about this a little bit last time. So Microsoft came out with their own language called J++. That was Java syntax that ran on top of Microsoft's Java virtual machine, which happened to be faster than Sun Microsystem's Java virtual machine on Windows, because Microsoft knew how to do the little efficiencies on their own operating system, right? Well, last time we mentioned that if you're somebody writing software in your underwear in grandma's basement, Microsoft steals your stuff and offers you $1 million for your trouble, you say yes and go buy pants. Sun Microsystems, this is a large established company, didn't just roll over and play dead. They fought back and they won. Okay, and that was the catalyst. Well, that was probably the starting of the catalyst for why Bill Gates stepped down as CEO of Microsoft. This is 3 CEOs ago. All right? But we know Bill Gates to be the Microsoft guy, right? That was what kicked him out, effectively. So Microsoft had to go back to the drawing board, and they created their own brand new language called C#. That was at the ACM conference in University of Illinois, Urbana-Champaign back then. That must have been in 2000-ish, probably 2000. And you always go to the Microsoft things at those because they give away the best free stuff. The other places are giving away bouncy balls and lanyards and stuff. Microsoft was giving away, enterprise copies, professional copies of their Visual Studio 6.0 product, which is like an $800 software product back then. Okay, and of course, all of us had pirated it before I learned to be ethical, right? Okay, so we just sold that on eBay. Back then, eBay was like, that was when eBay started. Okay, so that was like a free $500. Just get it to move quick, right? But in any case, I'm sitting in this thing, all that stuff I just said, don't do that. Do the opposite. Do the opposite of whatever that lesson was. Okay, but I'm sitting there as they're describing C# to me, and the guy up there might as well have been describing Java. But keep in mind that if we look at this chart here, all of these languages came from C. So Java took a lot of stuff from C++. Even though C# is extremely related to Java, they did do some things that are better than what Java did that then Java went back and incorporated into their own language. Okay, so C# is the real deal, and it's a good language. Okay, if you're doing Windows-only stuff, write it in .NET C#. If you want cross-platform stuff, write it in Java. All right, questions about any of the stuff we covered today? So I'm going to give you the rest of Chapter 1 to do over the weekend. And then I also want you to make sure that you have a working Python environment set up and have like a Hello World program or something like that running. I'll give you I'll find some tutorial out there that handles it for both Windows and Mac. So when we come back on Tuesday, all of you should be able to write Python programs on your computer.
On Monday, you mean?
Yeah, Monday, sorry. Should be able to write Python programs on your computer, so I can start doing Python stuff in class and give you homework assignments on it. Yeah?
Does Visual Studio work for that purpose?
For what, Python? Well, Visual Studio itself does not. There might be a plugin for the editor that will allow you to do Python. Yeah. You can do it if you want. I would recommend you use Atom. This is the editor I use. It's an editor called Atom, A-T-O-M. It's a pretty good one. It works for a bunch of different languages. It's great for all those web languages because once you name your file, whatever, it does color coding and stuff for it. So, but whatever you're happy with is fine. As long as you can run a Python program, it's all the same. Okay? And if you have a choice when you put Python on your computer, you want Python 3. There's Python 2.7 and there's Python 3. Whatever right now. They are both active, but we're doing Python 3 stuff. Okay? They are not 100% compatible. So if you get Python 2.7, a lot of the stuff we do in here will work, but you will have problems. So get Python 3. Whatever.